Hey everyone, welcome back to my channel EduVibe. In today's lesson, we're doing the next topic of the electromagnetic radiations. Not a topic, but we're doing the practice questions of the second part of this unit. So we are covering the total internal reflection with our lenses, diffraction, interference. We do the experiment called the Young's double-slit experiment. These whole topics we covered in today's lesson with some extra practice questions. Let's start with the first practice question from the total internal reflection. The question says that the light travels from the glass to air. The index of reflection for the glass is 1.51. The wavelength of the light in glass is 720 nanometers. Determine the critical angle at the glass air interference and the frequency of the light in air. Okay, so from where you can say that this is a total internal reflection quotient, from here that this goes from glass to air. So glass has the 1.51 and the air has 1.00. You go from the higher index of reflection to the lower index of reflection, which means we have a total internal reflection quotient. So we have to find the critical angle. Critical angle means we have to find the theta 1. So we have theta 2 in this case. So theta 2 is 90 degrees. We have wavelength, we have n1, and we have n2 is 1.00. So we have to find the theta 1, and you have to find use the same formula we have, Snell's law. N2 upon n1 is equal to sine theta 1 upon sine theta 2. You'll find the sine theta 1, which is theta c2, you can say. So sine theta 1 is equal to n2 upon n2 sine theta 2 upon n1. So theta 1 is, so you can do the reverse of sine. So n2 you have 1.0 sine 90 degrees, divide this by 1.51. When you solve this, you get your theta 1 or the critical angle about of 41.5 degrees. So this is your critical angle of the glass interference. And now you have to find the frequency. So for frequency, you have the formula. You have a V is equal to frequency times wavelength. You have to find the frequency. So V. Okay. So they want the frequency of the light in air. So a type of air, but we have like a glass thing all. So we can do with the glass. So we can like do with this thing with the glass. So we have V of the glass and the wavelength of the glass. So both should be the glass ones, and we don't have the another thing which is the V. So for V we have to do some another work. So V is equal to C upon N, because you know the N is equal to C upon V. So you can find from here, so C is 3.0 10 raised to power 8 meter per second, N is 9.5, and we do with the glass. So when you solve this, you get about 1.9871 into 10 raised to power 8 meter per second. You have to put this over there. So 1.987 into 10 raised to power 8 meter per second. Divide this by the wavelength. We have 720. Nano has the value of 10 raised to power minus 9. So for frequency, you will get about 2.76 into 10 raised to power 14 hertz. So that's how you can find the frequency. You're not just doing like a find a critical angle. You can add the subparts sometimes. So that's all you have to do in these questions. Same formula used like the Snell's law. Let's move to the next one. So this question is from the lenses. So we have to follow the following objects and stretch the image and identify its radius, magnification, and the type. So it's beyond 2f. So we have object over there. So it's the arrow. So we have to make the something to get the image. So this is the like a converging lens. So I follow that the converging lens is raised. So firstly I parallel this line, this incident ray to the principal lenses, and then on the other side pass it to the principal focus. So right over there, this pass through the principal focus like this. And the thing I made that this pass to the principal focus on that side, so I'm like over there, and then this goes parallel to the principal axis. So to make the lines that they are both refracted ray like touch to each other. So you get the point over there, and this is like an inverted type image. So this is your image over there. If you want, so you can make the arrow. So this type of image you get, and this is image is like very smaller than the object, so your magnification is the diminished one. You get the diminished. For attitude you get about like inverted image, and for the type you get the real one, because this is a converging one. There's only one case in convergent lens 2 where you have a special case, but it's not like that case. So that's how you have to make them, but you can't get like a direct questions about making the ray diagram. You want, for your convenience, to make the diagram for in the method analysis questions. Sometimes when you get the theory questions related to that ray diagrams. So that's all you have to do, and just have to know that how can we make that diagrams. So let's move on to some mathematical analysis of the lenses questions. The question says a 2.6 meters tall object is 17.0 meter from a diverging lens with a focal length of 3.7 meters. Determine the vertices of the image, distance of the image from the lens, and the size of the image. So you can see in the one question you have multiple things. So firstly, then this is a diverging lens. Diverging lens means that your focal length should be less than 0, which means should be negative. So this one should be negative 3.7 meters. 2.6 meter tall, which is your object's height dimension. HO, and that object is 17.0 from the divergent lens, so this is your DO. Both should be in positive, so you have to be in positive. You have to find the distance of the image, which is DI. You have to find the size of the image, which is HI. So this both thing you have to find. Characteristics of the image, so this is divergent lens, they always have the same characteristics. So characteristics of the divergent lens will be the virtual, diminished, and the upright image. These are the same for the divergent always. So for the next part, you have to find the DI. So very hard to find. You have a focal length, you have a DO, so you can use the mirror formula or the lens formula to get your DI. Use this. 1 upon DI is equal to 1 upon F minus 1 upon DO. So 1 upon DI is equal to 1 upon minus 3.7 meters minus 1 upon 17.0 meters. So 1 upon DI you get minus 0.329 meters minus 1, and you reverse the reciprocal of this, you get minus 3.0 meters, your DI. So this is your DI, and that negative sign represents that this is your virtual image, which is that the virtual image because we have a divergence. So you have the two parts done. Now you have to do the C part, which is the size of the image. For the size of the image, you want something else, because you have HO. If you have HI, so you can find it by the magnification, because magnification is equal to HI upon HO, from where you can find the HI, which is M times HO, but you don't have magnification. You can find the magnification with that much formula, which is minus DI upon DO. Because that three things are equal to each other, so you can use the anything from here. So you have my DI, which is minus 3.0 meters, divided this by DO, which is 17.0 meters. You can solve this as minus positive, so 0.17874 and no units. So you get the magnification over there. Put this magnification over there and get your answer. So 0.1784 and your HO, which is 2.0 or 2.6 meters. So you get your HI of about 0.46 meters. And you see, you get this is in positive because you have a upright image. And you get a diminished image because your m is less than 1. That all three things can be also be, you can do with, if you know sign convention, you can find this all three things with that too. So that's the thing you have to do. This question involves so many words, so this is about the 4 marks question you will get. And this is an easy type of question. You just want to know the sign conventions. The formula is on your formula sheet, so that's all you have to do. Next question we have. Okay, the next question is from the unsurface experiment, because this formula we had done, the formula when we done, so we have the graph question of that formula always when we're doing that thing. So using reference analysis, determine the separation distance d between the two slits. We have to find a d. Okay, so what we have, so the students set up the double slit experiment apparatus, examine how the angle of diffraction between the central maximum to the first order maximum. So they mention the first order maximum, so the n is equal to 1 here. So and the wave varies when the wavelength of the light source changes. So they graph the thing. So we have thing over there. So this is the wavelength on the x-axis, and we have a sine of angle of diffraction, which is your sine theta in your y-axis, and you have to get the very much line, and you have to find the do some 2 points from here, get the slope and get the answer. But firstly, we have to know that what slope is equal to. So your wavelength is equal to the d sine theta upon n. So sine theta is like on the y-axis, so sine theta should be stays over there like this, and you get about n wavelength upon d. Also your wavelength is your x-axis, so wavelength has been separated from here, so n upon d times wavelength. So this is your y, this is your x, and this n upon d is your slope. So your slope is equal to n upon d, and you have to find the d. So what's that? N upon slope. You know your n is, which is 1. You want to find the slope. So for the slope, you can use the formula y2 minus y1 upon x2 minus x1. Same thing we did, but just the same different formulas we always did. So that the 2 points from the graph. So if I take 2 points, so my first point should be something over there I take, but you can take any other point, but like you get the approximation answer, and there's a number of answers that right, and the other rounded values you get. So that's the thing you have to do. So this is same like 510 nanometers and 0.2800. This is x1, this is y1. The nanometer should be over there because we have a wavelength. And the other point I take something over there, this point. So this point is 2670 nanometers and 0.3700. So the other point. So this is your x2, y2. Put that points. So you get 0.3700 minus 0.2800, and this whole thing is multiplied by 670 minus 510, and I take nanometers in common, so I write it over there, but you have to not be nanometers, you have to like meters. So nano has a value of 10 raised to minus 9, and this is meters. So you get your slope when you calculate this about 562,500 meters, and you get like about -1, something like this. So you have to put this over there now. So 562,500 meters minus 1. You get about your d of about 1.78 into 10 raised to power minus 6 meters. If you get 1.75, 1.70, all are the right answers, but not be like way different answer. So that answer should be around that value, not very like 3.4. So that's the answer, and you have to do like very much well. You get as much accurate graph in the examinations or a diploma, but like in this you have like not very accurate graph. So that's the all thing you have to do and get your D. You always have graph question when you do one major formula in the units, like in physics. So let's move on to the next question we have from the small angle approximation, I think. So monochrome light of 580 nanometers is passed through two narrow slits imprinted onto the sheet of the cardboard The distance between slits are 6.7 into 10 raised to minus 4 meters. This maxima is 1.12 into 10 raised to minus 3 meters. Determine the distance between the slits and the screen. What you have to find. So from the slits and the screen, there is a called L. You have to find the L in this. Distance between the maxima is. So maxima, what is called maxima? Maxima is the X. So maxima is the bright spot. So from the maxima, any point which is maximum, from the any central point, you get your X. So this is your X. They I need to you. So this is your X. And the one thing you have the distance between the slits. So between the slits, the distance between the slits is your D. So you also have a D mention over there. And the wavelength, this is your wavelength, 580 into 10 raised to minus 9 meters, which is nano. So that's all you have, but you have to find the L. But before that, you have to check the angle. The angle is less than 10 degrees or not. So check the angle with that formula, because we don't have like L, so we can't use the tan theta formula. So this is like this. So sine theta is equal to n wavelength upon t. So theta is equal to sine minus 1 n wavelength upon d. So sine minus 1 n. What is n? So they not mention the n, so they just mention the maxima. So it means there is a order fringe of 1. So you can take n is equal to 1 directly. So I take n is equal to 1 in this, and 580 into 10 raised to power minus 9 meters. Divide this by the 6.7 into 10 raised to minus 4 meters, which is your d. You get a theta of 0.049599 degrees. This is less than 10 degrees, but there's nothing to do with now. So you just find the L from here. So L is equal to h upon tan theta. So h you have about 1.12 to 10 raised to minus 3 meters. Tan you have about 0.049599 degrees. So when you solve this, you get about 1.29 meters, which is 1.32 centimeters. So this is your length. You do some work and you get your L. So you just know about like in the like language of English that what's that thing that distance between the slits is. D, and the distance between the maxima is L. So that's all thing you have to do now when you do the actually questions like this. You're not like given that x is equal to not. You have to know that what thing is what. So that's all you have to do, and we have one more question to do. So we have this question from the like I do when the diffraction gradient we do. So there's questions like this, lines per centimeters we do in the when we do that topic. So here we have a slits per meter. So how we can deal with that questions, I'll tell you later. Okay, the monoponoidal electromagnetic radiation with a frequency of 5.090 in 10 raised to 14 Hz is shown through a diffraction gradient with the 2002 slits per meter. The angular diffraction to the third order maximum is we have to find. So basically we have to find the theta. And we have n is equal to 3. We have a frequency 2. So basically we don't have wavelength, but we have the frequency, and we also know the C because we know that C is equal to the frequency times wavelength. So from here you can solve for the wavelength, which is C upon F. So wavelength is equal to 3.0 raised to power 8 meter per second divided by the 5.90 10 raised to power 14 hertz. You get your wavelength of about 5.0847 to 10 raised to power minus 7 meters. This is your wavelength, and you have to find the theta. So you again have this formula now, and that sine theta is equal to this. Theta is equal to sine minus 1 and wavelength upon t. So put the things down, and 3 wavelength you get 5.084 to 10 raised to power minus 7 meters. What's the d? Now here's the thing. Your d should be this, but this should be in like 1 upon d form. So you have to find for d. So you do with the 1 upon this whole term. If it is slits per minute, you have lines per minute, but make sure your meter or centimeter should be same. Like in all questions you have a meters, this should be also in meters. That we have to convert this thing. So d is equal to 5.00 10 raised to power minus 6 meters when you solve this. So put this over there, and at the end you get your theta of about 17.8 degrees. Twist this. So this is the answer. That d, you have to know how can we find, because this is 1 upon d, so you can convert this slits upon meter is equal to reciprocal of that. So you can find this from here. So that's all what you have to do with the diffraction gradient 2, and that's the topic we end with our last lesson, and we done the practices up to this. Now we, in the next lesson, we start with the another part, which is the modern physics, which is the last part of this, which is a small part 2, and we cover the couple of things in that, and then we do the practicals of that unit, and then we end with that unit with some diploma questions. So in the next video we start with the introduction to modern physics, then we move on to the another things. So till then, so that's all for this lesson. Learning is a way to vibe, learn smarter, not harder. Please like, share, and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till then, stay connected with EduVibe.